came across this in the woods. It would be a natural tree, isn't it? Let me just see. Why do we have to wire everything? We're just creating something beautiful. I think too often we're always obsessed with wiring pines in the standard shape that conforms to bonsai, but we can be a bit unconventional, and let's see how we can make this look like a real miniature tree without going to the lengths of doing too much wiring, because the tree will look quite nice as it is. So what I would do is I would probably open it out a little more. So it's almost like a broom style pine, which for most people, pines are not usually grown as a broom style. But again, if you think of it, in nature you do find pines that grow like this. So let me just tidy up the dead twigs that are here. Maybe I will open it up with one piece of wood. Let me find some 1.5.
Hello, Leonidas.
Hi, can you hear me?
Hello, can you hear me?
Can you hear me now?
Yes, yes. How are you? Were you confused with this introduction with music and someone speaking about trees somewhere there?
Can you hear me?
Or yes,
Okay.
can you hear me now?
Yes.
Can you? Okay. Could you hear the music and the person who was speaking randomly about
Yes.
trees?
Yeah.
All right. I'll go. I have a new set today. How are you?
Fine, all is good here. The weather is nice. I don't know about there.
Here it's raining.
Okay, yeah. It's the season, right?
Well, not exactly. Here in Costa Rica is here. Well, April, May is kind of like in some parts it's the start of the rain, but in some others it's like it's not that much rain. But here I will put my camera here so you can see.
Okay.
But I'll turn this back also. Can you see?
I have a nice view, yes.
But so this is kind of like English weather basically at this time. I'll shut this one. But the thing is that like in the morning it was really sunny, so and it's around what 10 23 21 degrees outside. This is it's like kind of some sort of spring weather, but then later it gets a bit heavier, but then in June, we get a bit of sun again.
Mm-hmm.
And then October is the month that it rains the most.
Okay. And what about the lockdown there? How is that? How are things?
Well, things are funny, like things are like well, at the moment there is a lockdown, like apparently number of cases started to raise, and government said that we needed to still well to go again to the lockdown. Especially what they are kind of announcing is a collapse of the social security system, because like kind of it's probably getting saturated in terms of intensive care. But basically this is happening everywhere in the world, I think. Like oh, here is Ernesto. So at the moment is like there are some restrictions, and people are like I think people are starting to get used to the fear, basically. That's like my way of seeing this. And so there's a lot more confusion. Say?
That implies that you don't have so much fear now, right? Like if you're used to the fear, it means you don't account for the fear anymore, right?
Well, that is actually a very interesting question. For example, for Freddy, who lives in Honduras, where I think in Honduras the fear it's been there basically from decades. They have been living like that, but for Costa Rica is kind of new. So the funny thing is that people don't really know. And something that I am recalling is that, for example, well, in political Costa Rican history, we don't officially have an army. I mean, we don't have like we don't protect our borders. That's probably the most accurate way of saying it from what I understand at the moment. But all of our security resources, they go like for police and things like that. But this means that we should be having more money for education and health and other things. So this is the direct result of well, the direct result actually was the social security system, which is across borders. So we have one of the strongest system even in the world. Like even very rural places, they get access to very high quality clinical attention or anything related to healthcare. Even though our historical problem has been, for example, waiting lists for surgeries and some more expensive treatment, for example, like chemotherapy or things like that. However, it was going well, but now that I think there are two things that are combining. One is that we have one of the oldest populations. Our life expectancy reaches 84 years old for women, around that, if I remember well. Maybe I am not accurate for 2 or 3 years, but problem is that at the moment we have probably one of the highest population older than 65 years old, or even 70s or 90s, or a lot of people with hundreds. So these people, to take care of them, it gets really complicated, especially if they have diabetes or they have something else. Some of them are really pretty healthy, and this is probably one of the factors that it's giving us an advantage in terms that we are not having deaths like India, for example, or something like Brazil or things like that. But still is a threat, is a challenge to actually administer healthcare for this population. And
What is the population of Costa Rica again?
it's around 5 million people.
Okay.
It's at the moment it should be just above the 5 million.
Okay.
But in San Jose, it shouldn't be more than 2 million concentrated. So it's very, in this sense, it's very low. It's very easy to manage. But, and if you have the data from these people, the historical, well, the clinical records, then you could address something very nice for them. But still, there is the need of analyzing this data. Like there is the problem of privacy with the, or confidentiality with the data. And so it is still a problem to be solved in order to be able to analyze the data and be able to be more accurate in terms of decision making for healthcare. And yeah, well, yeah, the other thing is that well, some people I think because we are a small country, they just get really scared, and some of the I think one of the biggest mistakes that the campaign has addressed is actually to all the time be telling people to stay at home, and basically they don't advise people to do exercise, for example, and to eat well. Well, some people are I think Uber Eats have done a lot of money with all of this, because people are asking a delivery service all the time. But problem is that our biggest threat is actually cardiovascular disease. And so if you have people sitting down with diabetes and not doing anything and being very, very fearful of outside, they don't go outside, so it's a bomb, it's a clock. Basically, in the moment, people will start.
Measures apply in San Jose and in the suburbs. I mean, you have, I don't know, a lot of nature there. So I guess there can be places that people can go out.
That's, yeah, that.
If you're in the capital or not. So I don't know whether the same measures apply in all places in Costa Rica.
Well, the thing is that you, and for example, Ernesto is there, you have been in Costa Rica and you have been other places. But this is not the same for Costa Ricans, even though, I mean, even if you are in San Jose, very, 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 in the most dense city here, even though you have very nice parks and clean air, which is essential to all of these. So this is actually one of the resources that I can check, that I can see that it's an advantage for Costa Rica. However, how this is being interpreted by politicians and for citizenship is another story completely. So because one of the things is that actually parks are shut down, and one of our concerns was why Costa Rica, because of its history, the center of each of district has a park, a square park, and a church. I think it's very like Greece in this sense. Like you know you are in the center of the city because you know the church is facing west, and then so you have these open places where you can go and do exercise. You don't really need to be touching everybody. It's just having a walk or something. But these places are closed, and you see bars open. So and so there is a confusion there with how the political how do you say this, the policies are being applied, how the directions are being addressed. And I will not say that I mean, this is I think part of the uncertainty that the government has, probably, and a lot of other factors that get across. And so it's nobody really has a clear way of how to get us out of here, basically, I think. So I think it's just a matter of being patient and just they register basically everything that's going on. And I think at some point data will be released, and so if we can collect some other data of to observe what's going on, but maybe, yeah, it's a lot of things, and I think Costa Rica is one of probably it's easy going in all of these, but well, in Nicaragua and El Salvador and Honduras, things are very tense at the moment, I think.
What about Chile?
I mean, it's okay. The number of positive PCR is decreasing in spite of the large number of vaccinated persons. We have now 8 million of persons vaccinated.
Okay.
I don't know how many are the second dose, but in general, it's a large percentage. In Chile, we are 17 million. So, on the other hand, in spite of the quarantine, the government allowed to make exercise between 6 a.m. and 9 a.m. So it's full of people during the morning. Full of people is incredible. In bike or running, etc. This is across the country. Although it's winter in the south, but it's okay. Now we have not a lot of counties in quarantine, so people is more or less becoming more free. In particular, in 2 weeks we have an election, a very important election. So it's, I suppose the election will be held in 2 weeks. So it's important. Yeah, yeah, more or less the things are.
The elections are going to be physical.
Yes. Yes.
We'll go there, let's say.
Yes.
So
Yes. And it was the case some months ago with the national referendum. So it was physical also, and the percentage of persons who attend the election was more or less in general, in average, 60%, something like that. And in the past, without pandemic, it was more or less the equivalent, even less percent. So the only thing which don't worry is the government, but that is other things. And on the other hand, one of the, I don't know, important issues is that now we have this, the parliament introduced a law, the law was approved to take, by the third time, to take the 10% of your money in for pension. 10%, most 10%. So until now, I think 10 million or maybe more workers and professionals, etc., they took 30% of the money. Yeah. This is more or less the situation. If it's not a mystery, but we increased 6% last month. But I suppose this is due to the vaccination and to the money which is circulating Yeah. Yeah. This is more or less the situation. It's a little bit crazy. It's a paradoxical situation, but yeah, it's paradoxical because the government does arrive to take advantage of the percentage of vaccination. I mean, declarations and statements of person for government or person from the right are really stupid. And it's incredible, really incredible. I mean, on the other hand, I mean, if we believe, I don't believe, but if we believe the International Monetary Fund or something like that, no? These institutions say, okay, Chile have a lot of money outside the country. It's an incredible quantity of money, and Chile can give money to all citizens without problem for the future, and the government refuses to do that. And so this is because the parliament approved a third occasion that people can take the money for the pensions. And this is a political issue because in principle, I mean, the perception is for most of the population, our pension system, I mean, the perception is it is a bad system. It's a individual capitalization. So some people start to say that with 30% of money outside of the system, maybe this pension system will, I don't know, will crash or something like that. We will see what happens, but this is more or less the situation. So it's a crazy situation. It's a crazy situation, but yeah.
Well, I think yeah, it can be crazy, and it can be. I think there is a lot of confusion in across borders. Anyway, it's like, and there is, I think, a lot of questions of, for example, vaccination, and but also very basic things like. I think one of the questions that I got the other day was about, well, what do people think in terms of the ones that are afraid of vaccination, for example, the ones that don't want to have vaccination, and there is a lot of information going out threatening these people, and it's funny because it has actually a pattern in social media, and with fake news specifically. And then you have the people who actually really want to get vaccinated, and then you have fake news going in the direction of like vaccination is not going like it's like people are stealing these injections, or people are not going to have the vaccination, and then people are freaking out because of the fear of not being able to get vaccinated. So, but I think also, and this is one of the reasons why I actually wanted to start all of this year with what is a clinical trial, because it's actually trying to, or start deliberating of what are we observing, how we observe, and how we interpret this evidence, and when we actually take decisions or take actions from this evidence. So, and last meeting, we also had a very interesting debate going deep in what is a bias, which I think it was very, very fruitful discussion. And I think we have the responsibility of writing up all of what it has been said, and to be able to cultivate this forum in this sense. So, and now I think it will be very interesting to wrap up a bit from what we have been discussing so far with Leonidas in saying, in terms of, okay, so what are we actually validating with these trials? And I know, and I think I am facing this in terms of also of diagnose, because I think the first, probably how I and I would like to say this in a very clear way, because especially for Latin America, that we don't have these habits or this culture of clinical research, or even and I will say basically the infrastructure of supporting and manufacturing and producing systematically these products of research, of pieces of research that can fundament the different options of decision making that the government has to make. So what I want to say here is that and I think this was something that we came across in the first session that we had this year, especially with Freddy, when he wanted to ask about, so what can we do in order to model this situation, for example, with what is going on with COVID-19. But we stated from there that we wanted that we actually need to start describing the prevalences or the incidences. So in order to be able to see what is going on first and then go beyond. And I think the diagnostic is actually at the beginning, in order to, it's the first question that we have. So this is probably why I am saying that to derive the profile in each country is fundamental, because then we can actually elucidate in a better way how to diagnose whatever we want to diagnose. So probably this is the question that we want to go more deep in detail today. So I'll give you, Leonidas, your right to talk now then.
Fact that we all know that it's very hard. Can you hear me?
Okay, yeah, can we test? Can you start over, because we couldn't hear just the beginning.
Can you hear me now?
Yeah, now it's good. Thank you.
Yeah, I don't have many to add about specifically COVID-19, the COVID-19 situation. The only thing I can say is the obvious, that the knowledge of prevalence is tricky, because it's not, it's a contagious state. So it's hard to know at any given moment how many people are having the disease. So it's, I'm not sure how to have an accurate estimate of that. But if I am to start my presentation, then I can talk a little bit about biomarkers in a more general framework, not in a COVID configuration. So for that I'm not touching it. So should I share my slides, or?
Yeah, let me give you let me give you permission. I'm sorry, I didn't do it before.
It's okay.
Yes, actually, this is good that you are clarifying on that note of this thing about COVID, because this is actually what I wanted to emphasize, that this is not necessarily only going to be solving anything about COVID in the very immediate time. Actually, this is part of all of these forum where we get grounded in the terms of that we need actually to start learning how we observe the way how we observe the way we are living in our each countries. And so well, United States and somehow has been developing a lot of this research, and in Europe and other countries, but we are still starting in here in Latin America. So it's a good way to start to actually say, well, with COVID, there is a lot still to learn about, and I think there will be probably a long run with that. But so, okay, let's start with what you have to ask today, Leonidas, and thank you for having this time with us.
So you can hear me, right?
Yes, and thank you to Ernesto for being here. I think it would be a wonderful discussion then. Okay. Thank you.
Sure. So today I'm going to be talking about the discovery and the assessment of the accuracy of non-monotone markers, and I will explain what a non-monotone marker is in a little while. So the outline of my presentation is the following. I will start with the concepts of biomarker discovery and evaluation, biomarker evaluation. We'll discuss a new measure and some theory and some examples. Then we will proceed to estimation of cutoffs for an ROC analog when dealing with improper markers, and we'll visit both parametric and non-parametric approaches. Then we will see how these methods apply to real data sets, and we're gonna have a brief discussion about our simulations. And at the end, if we have some time, we can visit some fun historical facts about some aspects of the theory. So, motivating the problem, high throughput technologies like mass spectrometry and protein microarrays are commonly used for biomarker discovery. These technologies typically provide a very large set of candidate markers that initially need to be ranked based on some criteria. Common criteria are the AUC and the sensitivity at a given specificity, or the specificity at a given sensitivity at the clinically affordable level. And while these criteria enjoy broad acceptance in both the statistical and the clinical literature, they fail to capture biomarkers of improper behavior. When the ranking is based on the AUC, then the scores of the healthy, which we denote with X, and the scores of the diseased, which we denote with Y, are assumed to be stochastically ordered, namely X is less than Y. And let's have some background about the ROC curve. It is the most popular statistical tool for the evaluation of continuous biomarkers. And again, if we denote with X the scores of the healthy and with Y the scores of the diseased, then the sensitivity of a biomarker at a given cutoff C is the probability that Y, namely the scores of the diseased, are higher than C. That is also known as the true positive fraction. Then the specificity that also depends on the cutoff C is the probability that X, namely the scores of the healthy, are lower than C, an arbitrary cutoff, and that turns out to be equal to 1 minus the false positive rate. Now, note that both the sensitivity and the specificity depend on a cutoff C, on an arbitrary threshold or cutoff C. And for any given cutoff C, I can get a pair of sensitivity and specificity. Scanning now the cutoff on the real line will allow me to get infinite pairs of TPRs and FPRs. And if I plot them on the plane, I get the so-called ROC curve. It can be shown that the ROC can be written as a function of the CDFs, or equivalently as a function of the survival functions of the random variables Y and X. And here are 3 examples. We should look at them row-wise. So let's assume that the blue distribution is the distribution of the scores, of the biomarker scores for the healthy group. And the red density, the red distribution, is the PDF for the random variable that refers to the biomarker scores for the diseased group. We see here that the diseased population tends to exhibit somewhat higher values compared to the healthy population. And the corresponding ROC curve for this configuration is given on the right. So it's this ROC. Now, if we separate these densities a bit more, so we're focusing on on the middle row here, the middle panels. So if we separate them, if we separate the densities a bit more, we can see that the area under the ROC curve inflates a bit. And if we separate them even further, then the inflation is even larger. So at the one extreme, where the two densities are completely separated, namely they do not overlap at all, then the ROC starts from 0, 0, goes all the way up to 0, 1, and then ends up to the corner of 1, 1. So this implies that the area under it is equal to 1. And at the other extreme, if those two densities completely overlap, then the ROC coincides with the main diagonal of the unit square. And this in turn implies an area under the ROC equal to 0.5. However, the ROC operates under a stochastic ordering assumption. Loosely speaking, this implies that either one of the following is true. The higher the biomarker score, then the higher our suspicion for the disease, or the lower the biomarker score, the higher our suspicion for the disease is. It is usual and plausible for clinical investigators to assume that biomarker scores are elevated in the presence of the disease as a reaction of the organism. Namely, you can produce a higher level of, say, a specific protein in several cancer settings because the body is trying to react to the cancer. Even the opposite, which is more rare, has been dealt with in the literature and can be handled based on traditional ROC criteria. There is, for example, in Farman et al. 2018, an example, a metabolite study that refers to the detection of early-stage pancreatic ductal adenocarcinoma, also known as PDAC, in which some metabolites exhibit the opposite direction, namely the lower the biomarker score, then the stronger our suspicion for PDAC is. There could be settings, however, that relying on such an assumption of a single directionality may lead to dismissing potentially very useful or even excellent biomarkers. Namely, there may be settings in which both very high and very low measurements are indicative of the disease state, while controls lie within a healthy zone in between. Let's see some examples. Studies associating lung cancer with levels of prosurfactant protein B, for which both non-detectable, namely very low biomarker scores, and higher levels of prosurfactant protein B are being associated with the disease. Namely, very low scores of this protein, prosurfactant protein B, and very high scores have something to say about the presence of the disease, specifically lung cancer. In particular, decreased concentrations of that protein are associated with acute respiratory distress syndrome, lung injury induced by endotoxins, and late asthmatic response. Furthermore, lung surfactant protein B gene expression levels have been shown to decrease in mice exposed to nickel, which is an occupational hazard for lung cancer. This suggests that decreased levels of that biomarker may reflect pathologic conditions that are associated with an increased cancer risk. Other examples may include hepatic, breast, and urinary bladder and esophageal carcinomas that are related to these markers over here, which are generally downregulated in these cases. However, these markers may increase during the progression of esophageal squamous cell carcinoma, as is mentioned in Biot in 2012. Namely, there are examples in the literature that illustrate that this stochastic ordering assumption can be violated. And that, however, does not mean that we should blind ourselves to such markers and completely discard them. Let's now focus on our discovery part. Let's assume that we have n biomarkers in a list. What is a criterion to rely on so that we can sort them based on their discriminatory capacity regardless of their dimensionality? Namely, what is a criterion that is immune to any directionality and thus immune to the stochastic ordering assumption? In other words, in simpler words, what is a criterion that will allow us to capture all biomarkers for which higher measurements are more indicative of the disease and capture all biomarkers for which lower measurements are more indicative of the disease, and capture all biomarkers that do not have a single directionality, i.e., diseased individuals exhibit very high or very low values, while controls are in a healthy range in between. Let's see one example. Let's focus again on these plots row-wise. In the upper panels, we have the so-called traditional setting, and we refer to a perfect biomarker, namely the distribution of the controls or the healthy group is denoted with a dashed line and is a normal shape distribution that we see on the top left panel. And the distribution of the disease is illustrated with a solid line. So we observe that there is no overlap between these two distributions. This is a case of a perfect biomarker. The ROC for this configuration is given on the right panel over here, the top right panel. We see that the area under the ROC is equal to 1. That's not a surprise. So everything is good here. That's the traditional setting we're all familiar with. However, on the lower panels, we have another story. We have the distribution of the disease again with a solid line, and the distribution of the controls with a dashed line that is lying in between. So here we also have no overlap between the two distributions, and the corresponding ROC is given in the bottom right panel of this figure. We observe that the ROC now does this zigzagging, has this zigzagging form, and the area under it is equal to 0.5. Note now that an area of 0.5 would refer to an uninformative marker, and that would drive us to completely discard such a marker. And to continue with some other measures or criteria for these two configurations, for the upper configuration, we have an AUC of 0.1. The Uden index is also 1, and the partial area under the curve, namely for any given range of FPRs, let's focus from 0 to 0.5, then that area, that partial area is B minus A, namely 0.5 minus 0, so it's 0.5. In the lower configuration, however, that still refers to a perfect marker, we have another story. We have that the AUC is 0.5, we have that the Uden index is 0.5, and we have that the partial area under this curve, and let's say again from 0 to 0.5, it is 0.5 times B minus A. Namely, even though in both situations we have a perfect biomarker, all criteria that we are based on to detect and to evaluate the performance of a biomarker are different. So what is it that remains the same? We cannot have, it is not appealing to have two perfect biomarkers and at the same time all criteria disagreeing with each other. So what remains the same? What remains the same is the length of the ROC, which is equal to 2 in both of these cases. Let's now study a little bit some properties regarding the length and whether it's and discuss whether it's a good measure of assessing, at least at the discovery level, whether a biomarker is promising or not. Let Y be a continuous marker, and let the sample sizes of the control group and the disease group be N0 and N1 respectively. The corresponding density have an analogous notation, and the length of the ROC is given by this expression over here. This can be written as in equation 1, and by some further manipulation, we can write this equation as the integral of the square root of the sum of the squared densities, where F1 is the density of the cases of the disease group, and F0 is the density of the healthy group. So that is somehow a friendly form. Now, some interesting things are the following. The length of the ROC is equal to square root of 2 if and only if the distribution of the disease is identical to that of the non-diseased. And that is a case of an uninformative marker. We can further show that the length of the ROC is equal to the square root of 2 if and only if the biomarker is uninformative, and that the length of the ROC is equal to 2 if and only if the biomarker is perfect. Now, it is easy to show that this quantity over here, the length of the ROC minus the square root of 2, is a phi divergence, and it's equivalent to the perimeter divergence measure studied in Österreicher in 2013. And we proceed with the following theorem. The following theorem shows that the length of the ROC curve remains the same when one considers the likelihood ratio of the ROC based on the marker y, which is the length of the ROC curve associated with the random variable w that involves this fraction. Namely, if we denote the length of the ROC curve obtained by using the untransformed y by Ly ROC and the length of the likelihood ratio ROC curve by Lw ROC, then the Lw ROC is equal to the Ly ROC. This is an important result because it illustrates that the length of the ROC for the untransformed data is unchanged if we consider the optimal ROC curve. Namely, we can link the length of the ROC to the length of the ROC to the optimal ROC. Of the ROC of the untransformed scores, the raw scores that we have, to the optimal ROC. Some remarks are that the length has the advantage of having an appealing geometrical interpretation. Moreover, we can link it to the AUC of the optimal likelihood ratio ROC. And if the likelihood ratio was known, then the AUC of the optimal ROC could be computed directly. This is almost never the case in practice, thus bounds may be useful to practitioners. So now let's focus on this configuration. Let's focus on the first plot, and let's assume convexity for now. So the area under the blue ROC here, to know the area under the blue ROC implies simply knowledge of the shaded area under convexity. So we can just omit this triangle, and we can simply configure this C in a different angle, namely have that C on the x-axis along with the B. And what we want to illustrate here is that the right panel, panel B, is equivalent to panel A, as long as we focus on the shaded area, since under convexity, we do not have to focus on the triangle that is under the diagonal of the unit square. So the right panel is geometrically equivalent to the left panel. So now let's see this result. The Ly ROC, namely the length of the ROC for the raw scores, let's assume that this is L, and also denote the AUC of the optimal ROC by AUCW. Then, if the L is between these two quantities, we have that the bounds of the AUCW, namely the area under the optimal ROC, is bounded by these two expressions, where S equals to the area of a circular segment with a chord length equal to square root of 2 and corresponding arc length equal to L. And furthermore, if L is between these two numbers, then we have that the bounds of the AUCW is, are given by 5. Now I know that this seems a bit complicated, but we will proceed to a graph so that we can explain better what's the meaning of that theorem. Let's focus on the first configuration. On the first configuration, we have this triangle A, B, and C, okay? And the ROC is illustrated with blue color. So it's a curve. Let's assume now, for the sake of simplicity and to convey the message better, that we have a rope, that is the ROC, a blue rope, that is tied up to the endpoints of this segment, B and C. And we want to force convexity. So we are interested now in finding how can we locate, how can we place that rope within this triangle so that the area under it is maximized, and how can we place the same rope of the same length again in the same triangle under convexity, whose endpoints are tied up to B and C, so that the area under it is minimized. We have two cases: if the length is larger than pi over 2, or if it's lower than pi over 2. So in the first case, the configuration that will maximize the area under that rope is this one. And this one involves also quartile over strip. That's what the previous theorem states. And the configuration of the same rope of the same length that will minimize the area under it is either this or this. These two are equivalent and they turn out to exhibit the same area under them. So this panel, the top left panel with the top middle panel and the top right panel, they all refer to the same rope with the same length, namely the same ROC under convexity and same in terms of length. So if now the length is shorter, then the configuration that will result in the maximized AUC is this one, while the two configurations that will result in the minimized AUCs are the bottom middle and bottom right panels. So this is what we illustrate here. We illustrate, that's the previous theorem, that the AUC can be between this and that value. This is not a confidence interval, this is a bound. And if the length is between these two numbers, namely, if the length is short, we are here. So it can be between this and this value. While if the length is larger, then the bounds for the optimal AUC are given by equation 5, by inequality 5, and we are in this case. So we can intuitively also understand that if the length is, let's say, large, then we need to pile up that rope up to the point that is able to create a quartile of a circle and then to have a straight shot at point C. While if the length of the rope is shorter, then we need to directly start creating a segment, not a segment, a part of a circle, depending on the length that we have. And that's what drives the bounds of the AUC, of the optimal AUC. Now we have here a table for some examples. If the length, and again, I'm not talking about estimation yet. We don't have an estimate. We're just exploring what some values of the length mean regarding the optimal and the bounds of the optimal AUC. So the length of the ROC, if the length of the ROC is equal to the square root of 2, then the length has to be stretched from B to C. And that's it. There are no bounds there. It's the lower bound is 0.5 and the upper bound is 0.5. So there's no leeway there. If the length is a bit larger, 1.65, then the lower bound of the AUC is 0.77 and the upper bound is 0.87. As we move on to higher values, then the bounds increase. And if we have a perfect marker that involves a length of equal to 2, then again, there is no leeway, and that would involve the rope going from B to A and then from A to C with a straight shot, giving 0 leeway to the rope, and thus having a lower bound of the AUC equal to 1 and an upper bound of the AUC again equal to 1. Again, these are not confidence intervals. Now, what are the properties of the length in terms of asymptotic behavior? So if we operate under a null hypothesis of θ1 and being equal to θ0, where θ1 is the parameter vector that involves the distribution of the cases, and θ0 is the parameter vector that involves the distribution of the controls. So if these two are the same, namely under the null hypothesis, then this result holds, and this will allow us actually to test whether the null hypothesis can be rejected or not. And under the alternative hypothesis, where we have the alternative hypothesis implies that θ1 is not equal to θ0, then this result holds, given in 9, where the endpoints, where Ti, and that is involved in these vectors over here, Ti and Si are given by these integrals. It's kind of complicated computationally, but this implies also that we have some asymptotic normality for under the alternative hypothesis, and that would allow us to derive confidence intervals for the estimated length under some parametric assumptions. Now note that we are not assuming a specific distribution for the cases and the controls. This is a general framework that implies a parametric model, a separate parametric model for the two groups that is governed by θ1, θ0. Now, since the configuration is different, we have to kind of rethink what is the sensitivity and what is the specificity now. In our configuration, we are implying that the control group is in a safe zone in between, and that very high and very low values of a biomarker might be indicative of the disease, which visually can be represented by this plot over here, where with red we denote the density, the PDF of the disease, and with blue we denote the density for the controls. And for this configuration, it is appropriate to use two cutoffs as opposed to one. And namely, we have these two black lines. C1 is the first one, and C2 is the second one. C1 is the first cutoff, below which you are to be classified as positive. And above the second cutoff, you are also to be classified as positive. While in between the two cutoffs, you are to be classified as negative. This implies that the sensitivity now depends on two cutoffs, which can be written can be derived to be equal to this expression over here, while the specificity also depends on two cutoffs and is equal to this expression over here. Specifically, the specificity is the probability that given that you are in the blue group, what's the probability that you are in between the cutoffs? So that is F0 of C2, which is the second black line, minus F0 of C1. And the false positive rate can be easily derived to be equal to this equation over here. Here is an example of the sensitivity. So now, of course, since the sensitivity depends on two cutoffs and specificity also depends on two cutoffs, if we scan for all possible pairs of cutoffs, then we get a surface. For every given C1 and every given C2, we have a value of a sensitivity, and likewise for the specificity. So that's what we're doing here. This is the same plot visualized from four different angles for convenience. And this example refers to a configuration where the density of the controls is a normal distribution with a mean of 8 and a standard deviation of 1. And the density of the disease group is a two-component normal mixture, half and half, of a normal distribution with a mean of 6 and a standard deviation of 1, and another normal with a mean of 10 and a standard deviation of 1. So the controls are somewhat in between these two components. So the sensitivity surface now is looking something like that for this example. We have C1 on the x-axis, C2 on the y-axis, and the sensitivity on the z-axis. We observe now that when C1 is very small and C2 is very large, then the sensitivity will yield very low values since the mass of both densities is low, below C1 and beyond C2. In addition, if C1 is very close to C2, namely in this diagonal over here, if C1 is very close to C2, then it means that both cutoffs are converging to the same point, right? So then we expect that almost all individuals that are diseased will be categorized indeed as diseased because they are either above or below C1 and C2. Remember that the C1 and C2 now converge to the same point. So in this case, all individuals that are diseased will be categorized as such, since it is very likely that there will not be anyone between C1 and C2. And thus the sensitivity for those cutoffs is very high. That's why we have this red region over here. Now the story is somewhat flipped for the specificity surface, which looks like this for the same configuration. And now if we focus on the region where C1 and C2 are almost the same, if C1 is very close to C2, then we expect that almost all individuals that are healthy will be categorized as diseased. Why? Because the healthy individuals should be in between those two cutoffs. If those two cutoffs converge to one another, then there is no space, there's no leeway for the healthy individuals to to lie in between those two cutoffs. So they will be misclassified as diseased. That's why this surface is 0 at the neighborhood where the C1 and C2 are equal. Okay. Now, on the other hand, if they're very different, then that means that the surface will reach very high values, and eventually it will reach the value of 1. That would imply a configuration where the two cutoffs are severely separated, which implies that we naively categorize every individual as a control. That in turn implies that all healthy individuals will be correctly identified. That's why the specificity here is going to be equal to 1. That's why we see that this surface is attaining very high values at this area. Now I'm going to skip that. That's how we derive the optimal ROC. Essentially, we are saying that we can have the supremum of this sum of the F1 of C1 and S1 of C1 under this constraint, which is like essentially fixing the specificity or the sensitivity depending on what you want. I will proceed to this example to illustrate our point. There are two markers in this example, marker M1 and M2. So this is the blue one and the green one. Now, these two ROC curves refer to these markers that are being generated from the following configuration. The healthy group for both markers is a standard normal distribution, while the disease group for marker 1 is a normal distribution with a mean of 1 and standard deviation of 1, while the disease group for M2 is a normal distribution with a mean of 0 and a variance of 16. Now, by simply looking at these two ROC curves, we are tempted to conclude that the blue one, namely the biomarker that refers to the blue biomarker, to the blue ROC curve, is performing better compared to the biomarker that refers to the green ROC curve. It's the case that in almost all t values, the ROCT is higher, and it's kind of obvious that the area under the blue ROC is larger than the area under the green ROC. Note, however, that the length of the ROC1, namely the blue one, is 1.54, while the length of the green ROC is equal to 1.6701. So we now start to argue that the green ROC exhibits a higher length and thus might be more promising compared to the blue one that exhibits a lower length. But how can that be? From the density ratios, we see that the optimal ROC for M1 is based on the measurements themselves. Namely, for the blue ROC curve, there is no violation of the stochastic ordering assumption. Everything operates great there, and that's actually the optimal ROC. There is no transformation that would yield an improved ROC there. However, for the second marker, squaring the scores will yield the optimal ROC. Note that for the second marker, the healthy group is coming from a standard normal density, while the disease group exhibits exactly the same mean, but with a higher variance. Okay. So by squaring the scores, we can obtain the optimal ROC there. That can be proven. It's also related to the chi-square distribution. That optimal ROC that refers to the green one is now the red one. Namely, we can see that if we know how to transform the data, and this example is simply taking the square, we can attain an ROC of a transformation of the green biomarker that can outperform the blue one. Now, the thing to note is that the optimal ROC that is given in red color and that refers to the optimal ROC of the green marker outperforms almost everywhere the blue one. And the thing to note is that the length of the optimal ROC, namely the length of the red curve and the length of the green curve, are exactly the same. Namely, the red ROC curve is a different configuration of the same rope. So assume that we had this green rope tied up to 0 and 1 at its endpoints, and we're wondering how to place it in the unit square so that we can outperform, so that we can achieve a maximized area under it, and actually a maximized ROC for any given t. So that is a configuration that corresponds to the red ROC curve, and that actually outperforms the biomarker that is given in blue color. Now, the normality assumption regarding the estimation of the length is discussed in a parallel study done by Pereira et al. In 2020. And in this section, we will visit the Uden index. In the absence of any clinical insights, we would like to be able to estimate those two cutoffs, the C1 and C2. We proceed by maximizing a generalized version of the Uden index that is initially introduced by Dawson et al. In his PhD thesis. So the version of this Uden index involves, again, the well-known sum minus 1, the sum of the sensitivity and the specificity minus 1. However, this needs to be maximized with respect to both cutoffs. Now, under the assumption of normality, this breaks down to these two components, and it is conveniently, the cutoffs in this case can be written in closed forms. So the first cutoff is given by the minus and the second by the plus here. So by equation 23, we can derive closed form expressions for both cutoffs. And we can further proceed to obtain joint confidence regions for the sensitivity and the specificity at these pair of cutoffs. We simply transform to the real line the sensitivity and the specificity by using the inverse of phi. We proceed with the delta method to derive the variance of this delta E and the delta P likewise. And then we can consider this ellipse to find a joint confidence region for the delta E and the delta P. And once we find this 95% confidence region that is an ellipse, we back transform its coordinates using the inverse of that, namely phi. Now, the back transformed confidence region looks like an egg-shaped region, and that also accounts for the fact that the sensitivity and the specificity at the estimated cutoffs are in fact correlated. So the marginal confidence intervals for the sensitivity and the specificity can also be derived by back transforming with phi the confidence interval of the delta E, which is lying on the real line. Now, when parametric assumptions cannot be made, we can proceed non-parametrically using kernels. We can simply estimate the density of the controls and the density of the disease using two different kernel-based density estimates, as in equation 24. We explore a simple plug-in bandwidth for the kernel, but of course there are many options in the literature. One can proceed with cross-validation based bandwidths or more sophisticated techniques. And in order for us to obtain this egg-shaped confidence region, we incorporate a bootstrap algorithm. I will not go through all these steps, but the big picture here is that we obtain, using the bootstrap, the variance of the inverse phi of the sensitivity and the specificity. We create the ellipse on the plane that involves the R square, and then we back transform its coordinates to the ROC space, namely to the unit square. The resulting confidence region is often looks like an egg-shaped region. So through our data set now, we investigated the contribution of some autoantibodies as potential circulating biomarkers for the early detection of pancreatic ductal adenocarcinoma. Our data consists of two groups, 60 individuals that are healthy, and a PDAC group that consists of 73 individuals. And we have 121 antibodies, namely 121 biomarkers to assess. So here, each dot is one antibody. Okay. On the x-axis, we have the AUC, and on the y-axis, we have the proposed kernel-based length. And we illustrate here that the top performing antibody in terms of the length is actually going to be completely discarded, since it's if we are based on a traditional measure like the AUC, since the AUC is around 0.45 for that antibody. That would drive a practitioner or a clinical investigator to completely ignore that biomarker as uninformative, while it seems that based on our approach, it's the top performing biomarker in this set. Its ROC looks like that, which is, of course, very similar to the configuration that we started our presentation, that would refer to a non-monotone biomarker that is perfect. Of course, this antibody is not perfect, but it exhibits the same pattern of a very promising performance. On the right panel, we have the optimal ROC, namely we have the configuration of this rope that can maximize the sensitivity for any given specificity. We also note that if we are based on the traditional AUC and the traditional ROC analysis, the AUC is equal to 0.44 and the confidence interval is from 0.33 to 0.55. That implies an uninformative AUC, an insignificant AUC. That is a reason to discard the marker from your initial screening. And here is a complete visual analysis of this biomarker. On the top right panel, we have the two densities. The PDAC is this bimodal density, and the healthy group is given by this density around 0. The estimated cutoffs are illustrated with the dashed line. This is the estimated pair of sensitivity and specificity. We observe that the specificity is around 0.95, while the sensitivity is around 0.85. And this egg-shaped region is the 95% confidence region for the sensitivity and the specificity. These two surfaces are the surfaces of the sensitivity and the specificity for all possible cutoffs. Namely, in this axis we have C1, in this axis we have C2. As we scan C1, C2, we can visualize these two surfaces, which is like now the trade-off of the sensitivity and the specificity as we move along these two axes. As we move the cutoffs on these two axes, that's in analogy of the traditional ROC curve, where we move the single cutoff and we get a different trade-off of the sensitivity and the specificity. And here in the last row, we have another view of the sensitivity and the specificity for a better visualization. And with this black dot, we denote the point at which the Uden index is maximized. That is also referring to the optimal cutoffs that are illustrated in this top right panel. Now, there are also other examples. I will not go through the details. We have applied our approach into some other studies in which we also discussed that with the traditional AUC and the traditional ROC analysis, you would completely discard these biomarkers as uninformative, while with our approaches, we can see that you have a very promising approach of a specificity of around 0.92 and a sensitivity of around 0.76. Same story for another marker that refers to esophageal squamous cell carcinoma in some published data in 2011. Now let's proceed to our simulations. We have considered several scenarios. Let's assume now that the sample size for the healthy and the sample size for the diseased are 50-50, or 100 versus 100, or 200 versus 200. The configurations that we have considered are these, namely the AUC, the true AUC is 0.52, 0.55, all the way up to 0.76. And the healthy, the length of the ROC is said, the true value of the length is said to be equal to these values over here. And this is all under the normality assumption. So we see that the power that we have, now all this is under the normality assumption, and it is referring to a situation where the stochastic ordering assumption applies. namely the AUC and the traditional ROC would work here. And we compare the power of the length compared to against the Kolmogorov-Smirnov test, the Wilcoxon test, and the t-test. Of course, in this configuration, the t-test is the winner simply because it's kind of cheating. We're generating both densities to be normals, and the stochastic ordering assumption is holds up. So by definition, the t-test should win here. But we observe that the power of the length that is now estimated in a non-parametric way is doing decently. However, when we are dealing with improper settings, namely when the AUC is 0.5, however, the length is larger than that, and namely the stochastic ordering assumption is severely violated, it is very easy to win the t-test as is to win also the Wilcoxon test. Now, the power of the t-test is close to 0.05. The reason is that the power is actually the size now, since we consider distributions that have exactly the same mean, but really different variances. So the power of the t-test is doomed to lie on the nominal level of 0.05, simply because there is no difference in the means. And the same story holds up for the Wilcoxon test. A logical alternative is to proceed with the Kolmogorov-Smirnov test, but we see that consistently we outperform it if we use the length. So the conclusion is that the length of the ROC is an appropriate measure for biomarker discovery and can reveal all promising biomarkers and is also related to Phi divergence. We have linked it with the AUC of the optimal ROC, and when two cutoffs are appropriate, the sensitivity and the specificity are surfaces themselves. The decision-making cutoff for the decision-making cutoff estimation, we have considered the generalization of the Uden index that can be employed for cutoff estimation. The length of the RC is the same as the length of the corresponding optimal likelihood ratio RC, and we have provided inferences that are both parametric and kernel-based. And overall, this framework is useful when we are in need of ranking multiple biomarkers and assessing the potential of non-monotone ones, as well as when we are in need of cutoffs for such markers. And if we have some time, I can conclude some fun historical facts. This project essentially deals with an isoparametric problem. Namely, under the convexity assumption, how can we place a rope whose ends are tied up to specific points in order to maximize the area under it? And one cannot start talking about isoparametric problems without referring to the Dido's problem. The Roman poet Publius Vergilius Maro discusses the story of Queen Dido, the daughter of a Phoenician king of the 9th century BC. After the assassination of her husband, she fled to a haven near Tunis, and there she asked the local leader for as much land as could be possibly enclosed by the hide of a bull. Since the deal seemed very modest, the leader agreed. Dido cut the hide into narrow strips, tied them together, and encircled a large tract of land which became the city of Carthage. Dido faced the following mathematical problem, which is also known as the isoparametric problem. Find among all curves of given length the one which encloses maximal area. Dido found a solution intuitively. Around 150 BC, Zinodorus proved that if there exists a polygon with n corners, having the largest area among all other n-gons of a given perimeter, then this must be regular. Pappus of Alexandria in 300 AD, after an interesting preface concerning regular polygons, refers to some remarks upon the hexagonal form of the cells of honeycombs. The honeycomb conjecture states that the rectangular hexagonal grid or honeycomb is the best way to divide the surface into regions of equal area with the least total perimeter. So in this case, we are to prefer the left panel over the right panel or any other configuration that is not in terms of a hexagonal grid. Thomas Hales provided a formal proof of that in 1999, and he has also showed that he has also made discussions about the optimal piling of spheres under similar conditions. And these are interesting. These phenomena are also interestingly found in nature. For example, insect eyes, apart from the bees, I mean, the faucet of insect eyes, where we are in need, the insects are in need of maximal light sensing area, and at the same time, minimal saltwater material. And yeah, that's pretty much it. Here are my references. And This is a joint work with John Simikas, Gregory Chambers, Michaela Capello, Samir Hanas, and Ziding Feng. And thank you very much.
Thank you, Leonidas. Can you hear me?
I can hear you, yes.
Thank you for all of this journey of a lot of interesting ideas.
I try to be brief, so I don't think I have consumed a lot of time. So I think we're good.
All right, no, it's okay. And Ernesto, are you there?
Yes, I am here. Yeah.
Do you wanna say something?
I mean, it's an interesting word because it's of the, how can I say, of the geometrical interpretation. Certainly, I have not grasped a lot of ideas or details, but I want to try to understand. I don't know, maybe some basic things. Maybe for you is a.
I would like to ask some questions to Leonidas.
Okay.
Actually, like to clarify the talk. For example, the definition of because the talk is called, let me go back to the title, is Discovery and Assessment of
Non-monotone markers.
Non-monotone markers. So I wanted you to recall on the definition of non-monotone markers first.
Okay. So usually in the biomarker world, biologists and clinical investigators are very comfortable in assuming that a good biomarker that they are trying to find would have the following behavior. The higher its score, then the stronger the suspicion for the disease. So that's kind of like cholesterol, right? The higher it is, then probably that's more serious. So especially for cancer, that's what the investigator is comfortable to assume, that either the marker is useless, so the levels between the controls and the disease populations with respect to a specific biomarker are the same, which implies that the biomarker has nothing to say about the disease. It's not affected by the disease, so it's not useful to us. Or that the biomarker levels change simply because you have the disease. So in a biomarker study, it is a plausible assumption to say that the biomarker is good if, given that you have the disease, it's more likely that your scores are elevated compared to a healthy person, right? Now, in this talk, we were focusing on biomarkers that do not comply with this assumption, and that may comply with an assumption that states that it is dangerous to have either very high or a very low score.
All right.
So if you are very high, then that says something about cancer. But at the same time, if you are very low, that also says something about not being healthy. A good example might be, let's say, BMI. If it's very high, it's bad. If it's very low, it's also bad. Another example might be the hyper or hypothyroid. Very high values and very low values are at the same time bad. Or blood pressure. Very high and very low is also something that we can consider as bad, an abnormal state. While the healthy range is somewhere in between. Same goes with temperature. And also same goes with some biomarkers that I discussed in the slides that refer to proteins and antibodies. So I was discussing that if a biomarker conforms with that stochastic ordering assumption, that is a single directionality assumption, namely the higher the worse, then we have the tools to play around with these things, and we can actually shortlist them and find the most promising ones. But in this talk, I was arguing that if that assumption is not holding up, and we are dealing with biomarkers that may be of that nature, the dual nature, that very high and very low can be indicative of the disease, then we are doomed to miss those markers if we use the traditional ROC concept.
Right. So, and here, I think there are some other questions in relation to, well, the use of only one of these in order to diagnose a specific condition, or the combination of those, which is actually, I remember the talk that you gave last year that you were talking about this. And so, and I think the analytical question behind all of these is when we decide to use one of these markers in a very confident way. So if we have these problems that are some markers that are very straightforward, and we can actually see and decide very easy. But in other ones, the line is not maybe very clear. So, and so how we build up this balance between looking at specific things in order to make decisions or in relation to the therapy of this person or the condition, and which are the risks that we are undertaking here. Then this is probably what I want to grasp here, as all of the analytical process that you gave us is basically when we actually decide to use one of these, or when it's actually safe for us that at certain level we are actually dealing with a person that has certain type of diagnosis.
So the question is how to validate the biomarker and use it in a broader way. The way I understand it is that's what you're asking. And these things have been discussed in the literature. There are actually the 5 stages of biomarker validation given in a paper of Ziding-Feng and Margaret Pepe. They discuss 5 phases, phase 1 to phase 5. I think I have presented those stages in the previous talk. So you proceed from biomarker discovery, and then you gradually assess in larger populations, retrospectively and prospectively, until you reach at the level that you can test the performance of the biomarker at the general population. But these there are intermediate steps. So the talk that I just presented mainly focuses on the initial steps of biomarker discovery. So once you find a marker, it's not enough to say, okay, let's use that to the general population. Let's go with it. You really have to validate it externally, illustrate its behavior and its operating characteristics. And I mean, it's not that you found a biomarker out of a list of potential candidates that you have, and then you should just go ahead and assess it to the general population. There are specific phases that you have to go
through. Right, so that these are the graphics that you show us. Actually, something I wanted to ask you on the side of all of this, because I understand that you have the codes in order to produce all of these charts, and so I think it will be good to need these into the media that we are presenting here, so that we can actually show, or maybe in a different talk, how to build up these graphical ways of diagnosing data.
We're still working. I have like some codes, but we're still working on a user-friendly format. It's going to take some time, but we are hoping to have a nice user-friendly software that will allow investigators to analyze their data in a more rigorous way. Yeah.
Right. I think I will try on this one. So, and then, okay, so maybe you can just we can like recall a bit in one of like the main chart that you have in order to recall on the problem where there we see this spectrum, and I can see how like this is the initial parts in terms that we cannot actually decide only by looking at one biomarker or one marker that we are going to make very hard decisions on this. So I think I would like to go deeper on the problem of whether exactly what means that if we, for example, look at cholesterol in a specific level, and which are the risks that we have if we, I mean, like we have a cut point, and if we stress it, then we will have a certain results of positives or false, no, positives and negatives. And then if we have that cut point below that, then we will have another results in terms of sensitivity and specificity. So if we have, which is probably the question I want to grasp here, if we go, which is the risk that we have, or why is it important to do all of this analytical process in order to reduce the risk of maybe categorizing people in a positive condition or in a negative condition, and if we made mistakes on one of the other, that we can actually take into the risk of the research. So if we recall on this, so we can, I would like to basically detail on this problem so that portray in a better or more clear way exactly what we are doing by changing the cut point of when we decide this person has a certain condition from this point from up or this point down.
So
I don't know if I think I made a lot of
so in the traditional configuration, we have a situation that looks like this. Let's focus, let's say, in the middle. So we have the healthy group that we know that they're healthy. We know that, and we test them with a biomarker. Okay, so we measure something in their blood or whatever, and then we do the same for the disease group, for which we know that they have the disease. Okay, so now the question that you pose is where to place the cutoff. So let's see how the ROC is constructed. If we have a cutoff over here in 12, let's say, then every healthy individual is correctly identified. Is that true? Right. So here the specificity is 100%. Right. So below that cut, below 12, let's assume that our threshold is 12. So below that value, we make a decision that you're negative. And above that value, we make a decision that you're positive. That's a very bad cutoff, but let's see why. So we here are making a decision that every person that enters the room is healthy. Okay. However, by making that rule, by following that rule, we will correctly find all those that are healthy as healthy. Okay. So that the specificity here is 1. So a cutoff of 12 will correspond to this point over here. Because the specificity is 1. No, I'm sorry. It's gonna be here. because we have 0 false positives, I'm sorry. So we start from here. So you have 0 false positives here because you don't have any positive. You never decide a positive. Of course, you have 0 false positives. Okay. So as you move the cutoff, let's take it to the other extreme. If we have a cutoff at 1 or 0, then we consider that everyone is diseased.
Mm-hmm.
Okay, so we completely mess up with the healthy, but we have 100% accuracy for those that have the disease, right? So our sensitivity is 1. So here we are here. The sensitivity is 1. So as I move the cutoff from this direction to this, I'm sliding downwards in the ROC. I'm going this way. Okay, so for any given cutoff, I have a different trade-off of the TPR and FPR. The collection of all possible trade-offs, namely as I scan the cutoff for all infinite values here, will provide the ROC curve. So the ROC curve is what? Is a depiction of what can happen as I vary the cutoff. What is my trade-off? Now, if you want to focus on a specific cutoff, then you need to focus on a specific point here on the ROC curve. So a way to find what is the optimal cutoff is to say, what is that cutoff? So again, note that the sensitivity depends on the cutoff and the specificity also depends on the cutoff. A way to find what is the best cutoff is to say, what is that cutoff that will maximize the sum of the sensitivity and the specificity? There is such a sweet spot. And in this configuration, because they are normals with the same variance, just so it happens that that cutoff is where the two densities intersect. Okay, if they have unequal variances, then you have more than 2 intersections, so it's more complicated. But in the binormal setting, you can have this result here. You can have a closed form for the cutoff. Now that cutoff is called the Uden-based cutoff, and it is maximizing the sum of the sensitivity and the specificity. And that in the ROC space, which is a unit square, translates as the point on the ROC that will maximize the distance of the ROC, the vertical distance of the ROC, vertical in the sense that it is parallel to the y-axis. So the vertical distance of the ROC from the main diagonal. So here, the distance of the ROC from the main diagonal is very small. So it's not here. Here, it's kind of small as well. It should be around here. Now, all this discussion is under the assumption that if I do a mistake and I classify a healthy as diseased, and if I do a mistake and I classify a disease as healthy, then the cost is the same. Oftentimes, it's not the same. And if it's not the same, then you have to have different weights and you have to accommodate for that. And this concept of the maximized distance here is no longer applicable. You have to weight it based on the costs. For example, if the cost of someone being misclassified as diseased while he's healthy, he or she is healthy, and he's misclassified as diseased, and the cost is to have an ultrasound as a follow-up, and that's not such a big cost. If now you are diseased and I tell you to go home, and the result of that is you die in 6 months, that's a very big cost. You can think of it also in another way. If I have a cutoff that does a mistake and assesses a healthy individual to be naively to be diseased, so it's wrong. The individual is healthy, but the test is positive. If the follow-up is not just an ultrasound and is an invasive biopsy, that's a big cost. That also adds the stress, and it's a big cost because the biopsy might be very invasive in some cases. So you really have to place the cutoff in clinically affordable values, which drives discussion to exactly the presentation that I had done, not last year, but the first presentation that I had done, even in Costa Rica when I was there, that we were forcing the true class rates. We were forcing the sensitivity and the specificity to specific values. Namely, we didn't want to find the optimal cutoff. We were saying we can tolerate up to 7% false positives. We cannot go higher than that. I don't care what the optimal cutoff is. Maybe it is something that dictates a higher FPR, but I'm not willing to go there. So you can force specific sensitivity or specificity values. Namely, here you can say, I want to force a false positive rate of 0.2 simply because it's too costly to go beyond that. So I will make inferences around the corresponding sensitivity at that point alone. So what is the confidence interval of the sensitivity? If I fix that 0.2 as a false positive rate, what do I do? How is the marker doing in terms of sensitivity? Or vice versa. If I want to fix the sensitivity at 0.9, namely, it is very important that I will not miss any diseased individuals. And it's very important to not tell them to go home because maybe the disease is very invasive or very lethal. So you want to capture them. So you might want to force a 95% level of sensitivity and see how the marker is doing in terms of specificity or equivalently false positive rates. So yeah, these are all issues that mainly are dictated by the context and the setting of the disease you're studying.
How do you, I have a technical question. When you are going to force any values of sensitivity or specificity, how do you handle it in the software? You use a specific, the same formulas and then you get, how do you do it actually? How do you force the sensitivity?
You can so for every FPR you have a value for the sensitivity, so you can just the estimated, like it's straightforward how to get the corresponding sensitivity because it's a function of the ROC. The ROC itself provides that trade-off. The question is how to derive confidence intervals for the sensitivity given the specificity and vice versa. And for that we have a paper in Statistics in Medicine like a couple of years ago. I can send it to you if you're interested.
Yes, can you attach it to the references?
Yeah, I can send it to you through email.
Thank you. Yeah, we can have it there. So yeah, this is the thing why I think this is one of the basic talks for this space where we are discussing about how to undertake better research, better clinical research also. So, and I wanted to also having the opportunity that Ernesto is also here to link this with the last session talk that we had on bias, and this is probably one of the key aspects of this cut point. Whether I put it is also I mean, like how Leonidas is portraying us, it's from values. Which are my values in order to decide which are the results that I actually want because of the pitfalls or the risks that we are having in order that we take one decision or the other. And how this systematic error can affect the whole population. I remember once to see a figure about HIV once and comparing cutoffs that were used in the States and cutoffs that were used in Canada, for example. And I remember that just difference or US tend to use more more specific cut points, and so we get this brings more false positives because I remember that I don't know if I might you will correct me if I am saying something wrong, but the thing is that in order that we will be classifying a good percentage of people with positive results when they don't really have the disease. But in Canada, it was a difference of 100,000 people between the US and Canada just on cutoffs related to HIV diagnosis. I remember in this way. So for me, when you look at this on a very populational level, it brings up a more clarity in terms of the risk that we are taking, whether we actually move that cut point. So I will say that there is a lot of actually to undertake in a very experimental or analytical way, and how to maximize the area under the curve in order to actually have very, very clear results. And recalling that not all of the biomarkers are very clear, or not all the time the way of looking at disease or classifying therapies or conditions in order to get therapies are very clear, straightforward, only by looking at biomarkers. So how do you deal with this? Or I think with this is also very basic in some terms, very basic research. Or how do you see it, Leonidas? Do you actually use it, or do you integrate all the variables also in order when you actually apply it, or which is the experience that you have?
So that is a kind of complicated question because it will mainly refer to phase 5 biomarker studies in which you're interested in assessing a cutoff for the general population, in which stage you need to have the investigators assessing what are the costs for each mistake you do. So once you have the costs, it's a no-brainer. But if you don't have the cost, which is like the whole debate there is, what is the cost? What is the cost of a false positive and what is the cost of a false negative? What is the cost of the test itself? And that will dictate the differences in terms of cutoffs.
What do you think, Ernesto? Do you want to say something?
Yeah, maybe. Can I share the window?
Do you want to share?
Yeah, I used to write. It's more easy to write something. First, in order to understand what is the problem, and secondly, to illustrate you one problem which seems to be similar. I don't know if it is the same, but it seems to be similar. Okay.
Okay.
So you can explain me where is my this one. Okay. After following your discussion, Milena and Leonidas, you know the true state of the patient, no?
Yes.
I mean, you know a person is sick, or I don't know, have a disease or not.
Yes.
But maybe it is a stupid question, but this is always the case?
Excuse me?
This is always the case?
What do you mean by always now? Because like in biomarkers, if you want to assess the accuracy of a marker, that should be the case. Otherwise, we cannot assess the accuracy, right? You have to see how it's...
So this is a kind of a result which comes from a control, let's say, environment or experiment. This is the issue, no?
Yes.
Okay. So, because sorry, I don't know the terminology of a biomarker. So a biomarker is a kind of, correct me if if my interpretation is incorrect. So a biomarker is a kind of diagnostic test.
Yes.
We need to know the reliability, let's say, of
Yes.
the diagnostic test. So we are close in a room.
Yes.
We know the true state of patients,
Yes.
and okay. So it's a little bit different, but let me just explain you. Uh, in education, we have two similar problems. One problem related to the cutoff, and the other problem related to the reliability of the, let's say, diagnostic test. Related to the cutoff, for instance, in Chile, in education, we have a national test that, that intends to select students to enter to the Chilean university system. Okay.
Okay.
There are a lot of, specific things. For instance, each university is allowed to fix the cutoff. So, for instance, the better university, for instance, my university, Universidad de Chile, I don't know, other 2 or 3 universities. Let's say, just to as an example, to accept people for the medicine career, they put a very high cutoff. We have a test. This test is scored between, let's say, 200 and 850, and the mean is more or less 500, and the standard deviation is 50. So you can see that if I fix a cutoff of 750 or sometimes 800, it's very complicated to be accepted in the School of Medicine after you have or you fill the test, let's say, okay? So which is the problem? The problem is that we need, or this is a policy problem, we need to know how reliable or how perfect is the diagnostic test, which is the test. So we have just this problem. For instance, here we have, I don't know, let's say, people who was accepted at the School of Medicine. So this theta equal 1, this is just, I don't know, the indicator function, such that here some combination of the battery of tests is larger than, I don't know, 800. So theta equals 0. And the outcome people typically use is just to know, for instance, if the students, I don't know, complete pretty well the courses at the end of the first year, or if not. Or, for instance, maybe 1 equal 1 is just to say that your average score when you took 5 courses is at least equal to 4. Our scale is between 1 and 7, and 4 is the minimum to approve someone, and y equal to 0 if you don't arrive to that. So we know this part of the contingency table, this part of the contingency table, but this is unknown. And evidently, in order, as Milena asked, in order to know how, yes, in order to understand how, I don't know, precise is this cutoff or not, we have a big non-observability problem, because we are able to know this conditional distribution, but we are not able to know this conditional distribution. And we are lost. The problem is not possible in principle to be solved, because it's impossible to know this one, because we don't know either the true state of the students, they are smart students or not, for a School of Medicine, either we don't know if the test to hire students to the School of Medicine is a good test or not. It's almost similar to your problem, but in your case, you know the true state of the student.
Yes.
The other educational problem we have is the following, and we use a pretty similar um, hypothesis for us or assumption related to stochastic dominance. This is in the context of equating. So equating is just to you have two tests, form X, form Y of an standardized test, suppose, and you have score here, you have score here, and maybe you plot the distribution of test X plot, the distribution of test Y plot, and you say, okay, maybe this test in this part of the scale is more difficult than the other one, X and Y, but you don't know if this is the case because the students who take from X are smart than students who take from Y, or because test Y is more difficult than test X, and so on. And in particular, when it is the same population, when we have the same population, the same student who take this test and this test, the equating problem is just to equalize the quantize. And so this is, or let's put this one, and this is so just your formula that this is if minus one composed by G evaluated in some point. This is just the same formula you showed me. Oops. What happened? And this is, and so, which is the problem we have? And let me show you just a summary of the problem. For instance, in our country and in other countries also, it is apply a test to select people, I don't know, for instance, to universities or for hire a job, something like that. So you have a test X, okay? So you have a test X, and the test X is took by a group of persons we call P. But by security issues, for instance, it's not possible to publish this test because next year or next semester or whatever, there are other population of people who take a similar test Y, but because the consequences are important, for instance, to select good people for a specific job, it's not possible to publish this test. And so some people say, okay, I will take the form Y of the test. Theoretically, maybe both forms are equivalent, but this is just a theoretical issue. It's not possible to be sure about that. So what, in this case, what people assume or use, they use a set of common items or an anchor item that is answered by all people. And the rationality of that is to say that if you know the behavior of population P with respect to form X and to form A, you can use form A in order to have a kind of bridge to go from X to A and to A to Y in order to have, let's say, this kind of equality. Okay? But one of the things people assume is exactly the same hypothesis that people assume in observational study when they introduce the so-called propensity score condition. So they say, if I define theta equal 1, this is just an indicator to say that you belong to population P, so you answer from X, and theta equals 0, if the person belongs to population Q, namely he answered from Y. So people assume that the distribution of X, conditionally on the anchor and theta equal 1, this is equal to the distribution of X conditionally of the anchor and theta equals 0. So in a sense, you say, okay, conditionally on the anchor, we can ignore if the person answered this one or the person answered this one. At the end of the day, the distribution will be exactly the same. So this is exactly the same condition as a propensity score condition. And in the equating literature, this condition was introduced also by Rubin and Holland in a paper in 1982, something like that. So it's the same Rubin in other fields, let's say. So what we do in order to understand how strong is this condition was the following. And here we use a kind of monotonicity condition. We say, okay, I want to know this distribution. I will skip smaller than x just to have space. I want to know this distribution, and so I use the law of total probability. So I have this one times this left right plus this one times this. And on the other hand, the distribution of y given the anchor is equal to y given the anchor theta equal 1, the probability of theta equal 1 given a, it means this one, plus the distribution of y given a theta equals 0 times theta equals 0 given a. So, taking into account the observable information, we can identify and then estimate this distribution, because theta equal 1 is the indicator that the person belongs to population P. So he answered A and X. This is also identified. We know the proportion of person who belongs to population P and obtain some common score, but this is not identified. We don't know the behavior of people who answer test Y if they were answering test X. So this is not identified. Similarly, this is not identified, and this is identified. So what we do, we say, okay, in some examples, or in some cases, people can choose freely to take form X or form Y. For instance, in Chile, last year, in the science test to be admitted to universities, people can choose either the test of biology or either the test of physics. And some people, most of the students, the Chilean students, choose biology instead of physics. So we say, okay, we want to formalize this choice, and we will assume, this is just a belief, we will assume that students choose in a rational way, in the sense that if I am a student and I choose biology because I believe that choosing biology, my score will be better if I were choose physics or chemistry, whatever. So we introduce this monotonicity assumption. This distribution, T given A and theta equal 1, I will compare this one with this, A and theta equals 0. This one, wait. No, sorry. I need to, still one, sorry. And so this is, and I will compare with this distribution, y given t, a, and theta equal 1. So what I say, For those students who choose or who took test X, these students take test X because they believe that the probability to get at least an score equal to T is greater than if they were to choose the other test. And so this is a kind of monotonicity in the sense that this distribution, in a sense, dominate this one. And using this condition, which is a partial identification condition, we arrive to partially identify this true distribution and to make the equating, namely to put the quantiles or to equate the quantiles and to make some sort of conclusion. In this context, we use quite similar, it's not the same idea, but they are quite similar idea. And I want to understand better the rationale of your paper in order to see if those ideas helps to have a more clear comprehension of that. But this is the similar, or in the field of education, similar, wait, what happened here? Similar problems we have in which?
What I would say actually is that, well, it's interesting because well, earlier this morning I was thinking about the differences between the clinical context or the medical context and the education or the learning environment, and how these things are actually at some point at some, well, equivalent and somehow.
Mhm.
But what I will say, and I think this is kind of a question or a critique for both of the fields. It's actually, well, this is the use of a test, especially well in the clinical context. It will be a measure, a physical measure or a chemical measure, or even a biological measure, or a combination of all of those. And then in the educational or education context, context, we have a way of observing, like in both cases, it's actually a picture of the moment. And one of my questions will be, for example, if we compare blood with I don't know, educational performance or something like that, like a concept. I don't know I think Ernesto will have other concepts, but one of my first questions, it would be how consistent will be one to the other, or if they are consistently equivalent. Maybe I want to say something like that.
Oh, okay, yeah.
So one question will be in that sense. And if in education the test might be seen more, I will say there is a lot more variability in the education environment because of how thoughts can actually change in a matter of seconds. But blood wouldn't be changing that rapidly, maybe, but we will have to see it in a different way. So the thing here where I want to go is, in both cases, I think the analytical or the analysis of the risk should be performed as well after setting up those values where that actually Leonidas was addressing at the beginning. This is probably one of the key points where I think to undertake the ethical agreement first, even though this is a very complex process, I think is kind of the way where we actually find where how to assess us in a for therapeutical options, or even for, I don't know, maybe career options or other things. But then for education, I will say why we need actually to, and this was one of the questions that I have for Ernesto, why this is important, for the state to actually know how to measure the understanding of physics or mathematics or something like that. With these, I will say that there are actually scales that are different within the country and also compared within countries or between countries. We will say it will be different scales to apply in a way. But this is also the problem with clinical issues. I mean, if we recall the issue for the difference between Canada and the States with HIV. And I think it's happening even worse with the context that we have with, well, this environment that we have with COVID. And this is one of the things that everybody's saying, everybody's testing, but at the same time, and also vaccinating, but we don't still have any fundamental evidence for this. So we are still testing, I think, or experimenting. So this is one of the points that I would like to stress a bit more in terms of when the tests are useful and considering the risk that we have, even with the I will call these, and I think this is the invite for you to write, because this is what I call the classification problem, which I'm not the first in talking about this, obviously, especially if you're a statistician. Then it's like how we classify things and the problems that classifications bring with all of these. So one of the important keys points of this talk was actually to show that to decide or to classify a person whether it has a disease or not is actually a very complex or very elaborated analytical process, and that it's also needed with a lot of perspectives that drive a lot of different sources of bias that maybe should be taken into account as long as research grows, or as long as we actually manage to integrate other sources of information. So having said all of these, I want to thank you two for being here today. I think it's all of these. And today, at the beginning of this project, I actually wanted to go really fast, but now I am understanding that it's good to be meeting with maybe not that often, but very frequently, or at least each 15 days, I think is a very nice time. And so, because there is a lot of questions that are raised from all of these talks, and I think especially with you two, it's been very, very interesting how this has been meeting. So I think one of the ideas that I have for next meeting is actually, well, I have two options that I wanted to ask you. One is I do a recall on the 3 talks that we have delivered. And I wanted to summarize like key points and maybe present something from my own work. Or the other option is actually to leave this for the next session and to invite someone else. Maybe I was thinking Freddy, in order to have us to tell us about how is it in Honduras and how the issues that he's having in his work. But well, I want to know what you prefer to do in order to.
It's fine with me, whatever you think is best.
I'll just toss a coin then. Okay. Okay, then. So I'll process all of this video. I uploaded the one from last time, but we had a cut. I actually put an announcement in that part because we lost exactly when we were discussing, and I think we lost the track there. But I think it will be a very nice effort to, well, this is why I want to do this next meeting in order to wrap up things and be able to actually write part of the process that we are having. And so, because I think it's very rich in order, this part I am actually understanding that it's a kind of a calibrating language part. We are understanding each other and what we do and how the problems or the issues that we are interested. And then, well, it's just to be very systematic in the registration of all of these. So I think it's only the work of recording all of these and uploading. It's a good effort. But yeah, I want to see actually how these things can grow. So, well, anyway, thank you. And if you want to say something else, I'm very happy to listen. Or
Thank you for having and
Yeah, thank you very much.
accommodating all these talks, of course.
all right, I want to see you more excited, Leonidas.
It's here. It's like 7 o'clock, and it's.
No, I understand.
Yeah,
This is something I can say to you because I in the experiences in statistics is this thing on and off that you are abstracting and contextualizing things.
Yes.
So sometimes I think it's very heavy for the
Everything will be more vibrant if we are allowed to travel, so I can visit Costa Rica again.
Yeah,
yes. This is why I actually wanted to because I was thinking that this systematization process will help us to actually have a product so that we can request funding easily to show what we are doing and other things like that. So yeah, I agree with that. So I'll work on it. All right, thank you.
Thank you very much. Good night.
Bye, good night.
Have a good rest. Bye bye. Ciao, Milena. Bye bye.